this lecture, we'll introduce interpolating polynomial. You will see that with slight changes in the nature of polynomial, we can avoid the inversion of Vandermonde matrix and the overall calculation will be much easier. The basic idea is that in a polynomial interpolation, we have assumed the nature of polynomial as y equals ai x to the power I, where I is going from 0 to n. However, we can also define this polynomial as b naught plus j equals to 1 to n bj multiplied by product of x minus xi. And the idea that these two are equivalent, we have established in our last lecture, that if we have n plus 1 points and if we define an nth degree polynomial through this n plus 1 points, then the polynomials are same. So that idea we will explore and we will build, in this case, is what we call the Newton's interpolating polynomial, and we will end this discussion with an example of how to apply Newton's interpolating polynomial. Recall what we have discussed last time. We have seen that the straightforward way of finding the constants in a polynomial, that means a naught, a1, a2 up to an, this n plus 1 constants, is to satisfy this polynomial by this n plus 1 points xi was yi. When I do so, we get n plus 1 linear equations where my coefficient matrix is a Vandermonde matrix V, that is 1 x naught square x naught n, and the last row is 1 xn square xn to the power n. This matrix has a non-zero determinant that we have discussed last time, which means that we can have a V inverse, but this matrix is sometimes unstable, and also we want to avoid the inversion of such a compact matrix with very little scope of 0 and all. So with a matrix like that, it will take a long time in computation. So what we want to do, that we want to simplify this procedure. So our goal is that we modify this procedure in a way so that we can calculate the coefficients, this a0, a1, a2, etc. Easily. So let us see how we can do that. So we don't want to have a very big matrix inversion. So what we can do is that we want to exploit this idea that we have got last time, that if we have n plus 1 points and if we fit an nth degree polynomial through this n plus 1 points, then this polynomial is unique, which means that all nth degree polynomials passing through this xi, yi are just the same. So instead of writing the polynomial as y equals a0 plus a1x plus a2x square, etc., we write the polynomial as b0 plus b1 into x minus x0 plus b2 into x minus x0 multiplied by x minus x1, etc. And in bn, I have a bn multiplied by the product of x minus xi, where I goes from 0 to n minus 1. So now you can see that in this particular expression, this is also a polynomial. If I multiply each of these, I'll get a polynomial similar nature of this y equals a0 plus a1s, etc., etc. You can see that we have the power of x minimum is x to the power 0, that as in a0. Here also you will see that in b0 we have x to the power 0. Similarly, b1 x0 is x to the power 0, b2 x0 x1 is x to the power 0. So that is there. And then again, the maximum power is x to the power n. So here with bn, I have product of x minus xi. If I multiply all these x minus xi's here, I can see the maximum power of x will come in xn. So essentially this particular expression that b0 plus b1 x minus x0 etc. This is also an nth degree polynomial, same as y equals a0 plus a1 etc. So these two are nth degree polynomials, and if these two polynomials passes exactly through these xi, yi points, that means that these two polynomials will be exactly the same. They mean the same thing. So this is an idea that we want to exploit, and we'll see that the second polynomial, although it looks complicated, it will be much easier to calculate the coefficients b0, b1 etc. as compared to that of the calculation of a0, a1 etc. And this second polynomial, that what we see as b0 plus b1 x minus x0 plus b2 x minus x0 x minus x1, and this particular polynomial is known as Newton's interpolating polynomial. Here of course our goal at the end is to find the b0, b1, b2 up to bn, this n plus 1 coefficients, instead of the earlier we were finding a0, a1, a2, but now we are interested about this b0, b1, b2, all these coefficients. And we hope that the procedure for finding these bi's should be easier than finding the ai's. That means we don't have to invert the v matrix. So let us see that how we are going to get this coefficient b's. First of all, you can see that all the terms here in this Newton's polynomial, they contains an x minus x0. Only exception is the first term that does not have an x minus x0. b1 has an x minus x0, b2 has an x minus x0, and bn has an x minus x0. So all the terms will have an x minus x0 except the first one. So if I put x equal to x0, then what I get is y0 equals fx0 of course, and that is equals b0, because every other term will go to 0 at x equal to x0. So finding b0 is very easy. So we just have our first coefficient without doing pretty much anything, without inverting any matrix or anything. Now let us focus on the b1. Now you see that all the terms in this polynomial y equal to fx has this x minus x1 as a factor except the first two terms. So if I put x equal to x1 in this polynomial, then only these first two terms will survive, all other terms will go down to 0, which means that y1, which is f of x1, is given by b0 to b1 x1 minus x0, and that means b1 is this f of x1 minus f of x0 divided by x1 minus x0. F of x0 is the b0, so that is how this f of x0 is coming. And this particular expression we write in a simpler way with this f and a third bracket x1 x0, and we call this first finite difference. This term finite difference is very important, and we will discuss more about it when we come to the calculation of numerical derivatives. But this is the first finite difference. You can see that it is only the difference of y between 1 and 0 divided by difference of x between 1 and 0. Now I have b0 and b1. I want to go to b2. With the same idea, every term in this polynomial has x minus x2 except the first three terms. So if I put x equals x2, then only first three terms will survive. Everything else in this polynomial will go down to 0, which means we can write this f of x2 equals b0 plus b1 x2 minus x0 plus b2 x2 minus x0 into x2 minus x1. I can then simplify it. If I simplify it, I find that b2 equals y2 minus y1, divided by x2 minus x1. You can see this is very similar to this first finite difference. Similarly, the second term is y1 minus y0 divided by x1 minus x0. This is also another first finite difference divided by x2 minus x0, and I can write this as the first finite difference of x2 x1 minus first finite difference of x1 x0 and divided by x2 x0. So this particular expression, I name it as second finite difference, and within this third bracket I write these three terms x2 x1 x0. This is going to be the second finite difference of x2 x1 x0, and this expression is just given in terms of first finite difference. This is how I have the B2 now. So we can see that we can take one unknown at a time and we can calculate that relatively easily as compared to inversion of a complete matrix. In the same way, I can calculate B3, and we'll find that B3 will be the third finite difference. It will be x3 x2 x1 x0, and that will be written in terms of second finite difference. Second finite difference again written in terms of first finite difference. First finite difference is written in terms of the value of function. So we can proceed in this way, one unknown at a time. One unknown at a time is somewhat equivalent to inverting a triangular matrix, but at least we can agree here that inverting a triangular matrix is much easier than inverting a full Vandermonde matrix. In one unknown at a time, when you are calculating B0, you see that the first row of the matrix, this is our coefficient matrix, which is a lower triangular matrix. First row of the matrix only has 1 and rest 0. So B0 we can calculate directly, that B0 equals Y0. And then second row we have two terms, then rest 0. Eventually third row will have three terms and rest 0. And the last row will have full. But if we start from the top, that means B0, we can take one row at a time, and we don't have to invert the matrix directly. We can simply take one row at a time when we can calculate the unknowns B0, B1, etc. So this lower triangular system of equation, we can solve it eventually to get all the B's. Once we complete the solution, we can have this Y as f of x0. You remember that that was our B0 plus x minus x0 into f x1 x0 plus x minus x0 x minus x1 is f x2 x1 x0, etc, etc. And finally we have the product of x minus xi, and I have this f of xn xn1 etc that goes up to x0. Now it looks quite complicated, but we'll see that this is, in practice, this can be applied very easily. Let us see an example here. Let us take 5 data points, that is going from x equal to 1 to x equal to 2.2, and correspondingly y that goes from 0.765 to 0.110, and we try to fit a polynomial. This was an exercise problem in our last lecture. If you have attempted it, you know how to solve this problem inverting the V matrix. But now we will solve this problem using Newton's interpolating polynomial. So what we do in Newton's interpolating polynomial is that we create this table. We really don't talk about the coefficient matrix. We simply create this table. How? Here you see that in this column I have all the values of xi, in the next column I have all the values of yi. Then I make the next column is f of third bracket xi plus 1 xi, which means the first finite difference. And how do I get the first finite difference? This I'll get from this 0.620 minus 0.765 divided by 1.3 minus 1.0. So I take 0.620, I subtract 0.765 and I divide whatever I am getting from here by 1.3 minus 1.0. So this will give me first finite difference, and I see that that is coming as 0.48337057. Similarly, I find the first finite difference between 0.620, 0.455, and that gives me 0.5489. It goes on 0.455 and 0.281, it gives me minus 0.0578, and then 0.2818, 0.1103, and it gives me minus 0.5715. So now I have all the first finite differences. I go for the second finite difference. To get the second finite difference, I take the difference between these two, for instance here 0.4837, 0.5489. I take them and I divide once again this 1 and 1.6. After that, I have the second finite difference minus 0.1087. Similarly, I take 0.54 and 0.57. I divide that by 1.9 minus 1.3. I get 0.0494. I go on with this and I have 0.5786, 0.5715, and I have 0.0118 as my second finite difference. Once my second finite difference is done, I go the next column in my table, that is the third finite difference, and here I take this first two and difference from this xi to xi plus 2. Similarly, I take this second two, 0.049, 0.011, and once again difference of xi and xi plus 2. So I get our next column is 0.065, 0.0680. Then I go to the last column. Here I have two terms, so then I have my last column. So I have my last finite difference. This is my fourth finite difference. So this is the first, second, third, and fourth and final finite difference, that is 0.0018. So now I have populated this table. So I go back to this expression. I don't have to do anything else. Now the table is complete. I can directly write the polynomial. There is no further inversion of matrix or anything. I can directly write the polynomial y equals fx0. What is fx0? 0.0751977, that is my fx0. Then x minus x0 multiplied by f x1 x0. f x1 x0 I have calculated here, that is minus 0.4837. So minus 0.4837 etc. multiplied by x minus x0. x0 is 1, so x minus 1. Then x minus x0 multiplied by x minus x1 into f x2 x1 x0. x2 x1 x0 is the second finite difference and the first one of that. So this is my minus 0.1087 multiplied by x minus 1 and x minus 1.3. There will be no f here. Then I go to the next step here, 0.065874. So 0.065874 multiplied by x minus 1, x minus 1.3, x minus 1.6, and finally 0.0018 multiplied by x minus 1, x minus 1.3, x minus 1.6, x minus 1.9. So now I have the complete polynomial, and this is the answer. I don't have to do any further calculation or inversion of any matrix. So the procedure may look cumbersome, but with some practice you will see that it's only amounts to finishing this table, and it is certainly easier than inverting a matrix. So now for your exercise, you want to implement this procedure that we have just discussed in a computer. So first you write a pseudocode, and then you implement that in a computer, writing a computer program, and you fit this polynomial through the data points that we have just discussed through these 5 data points. And that's all for now. Thank you, and I'll see you in next class.